Hey everyone, and welcome to this explainer. Think about the last time you just looked up at a starry night sky. The sheer vastness of it can be totally overwhelming, right? Well, what if I told you that a telescope isn't just some giant magnifying glass for looking at stars? It's actually a literal machine designed to test the very boundaries of reality itself. Today, we're diving deep into the incredible physics and the honestly mind-boggling engineering marvels that let us peer across billions of light years, slice right through cosmic dust, and literally see backward in time.
So, here's our roadmap for today's journey. We'll start with the limits of our eyes, then talk about bending and catching light, seeing the invisible universe, beating Earth's atmosphere, and finally, looking at the ultimate cosmic observatories. Let's get right into it.
All right, Section 1, the limits of our eyes. To really grasp the unbelievable power of a telescope, we kind of have to start with a fundamental limit of our own human biology.
And the crucial point here is this. The human pupil, even when it's fully dilated in pitch-black darkness, maxes out at just 7 to 8 millimeters across. So why does that actually matter? Well, light from distant galaxies has been traveling through the freezing void of space for literally billions of years. By the time those photons actually reach Earth, they are incredibly sparse. They're super spread out. Because our pupil is so tiny, it severely restricts how much of that ancient light we can actually catch. It's kind of like, imagine your eye is a tiny little shot glass and you're trying to catch raindrops in an incredibly light drizzle. You're just not going to catch much, right? If you want to catch more rain, you need a vastly wider bucket.
So, to solve this biological bottleneck, humanity basically decided to outperform evolution. We invented a dedicated tool designed to vastly outcollect and outresolve our own natural vision. At its core, a telescope is really just a giant light bucket. By gathering a massive amount of electromagnetic radiation, which is really just the physics term for light, and bringing all those gathered photons to a sharp, concentrated focus, a telescope lets us observe ancient, faint objects that are literally billions of times too dim for our naked eyes to ever perceive.
Moving right along to Section 2, bending and catching light. Overcoming our biological limits kicked off an intense, centuries-long battle of optical engineering.
Now, what's really fascinating here is the showdown between the two main ways we've historically built these giant light buckets. Early telescopes, like the iconic ones Galileo used to spot the moons of Jupiter, were refractors. They used precisely shaped glass lenses to bend the incoming light, and they produced incredibly sharp images. But they had a massive physical flaw. Glass bends different colors of light at slightly different angles. This created these really frustrating, blurry color halos around stars, an optical flaw known as chromatic aberration. Plus, if you tried to build a truly massive lens, the glass physically sags under its own weight and completely ruins the focus. Then, the brilliant Isaac Newton comes along, and he swaps out the heavy glass lens for a curved mirror. These reflectors completely eliminated those blurry color halos, and, crucially, mirrors can be firmly supported from behind. This single breakthrough is exactly what allowed telescopes to eventually scale up from the size of a long tube to massive, building-sized giants.
Okay, Section 3, seeing the invisible universe. Because, as it turns out, the visible colors we can see are just a tiny, tiny fraction of the grand cosmic story.
And this beautifully illustrates a bit of a profound cosmic irony. You see, Earth's atmosphere does a magnificent job of protecting us from lethal radiation. But in doing so, it entirely blocks large chunks of the electromagnetic spectrum from ever reaching the ground. Visible light and radio waves. They reach our terrestrial telescopes just fine. But if you want to study the universe in highly energetic wavelengths, like X-rays pouring out of a black hole or gamma rays from an exploding star, you simply cannot do it from the surface of the Earth. The atmosphere is literally a brick wall to those wavelengths. You are physically forced to build specialized telescopes and launch them out into space, like the Chandra or Fermi observatories, just to catch those violent cosmic events.
Capturing infrared light is another absolutely essential superpower. Cool objects, dusty star-forming nurseries, and the very first primitive galaxies in the universe, they shine intensely in the infrared. But infrared is essentially heat, and this is exactly why we built the James Webb Space Telescope. To stop the telescope's own internal heat from completely blinding its super-sensitive sensors, Webb operates behind a tennis court-sized cryogenic sun shield. It acts like an SPF 1 million sunscreen. This astonishing engineering is what lets us literally peer straight through towering clouds of opaque cosmic dust, unlocking secrets of the universe that were completely invisible to us before.
All right, let's head back down to the ground for Section 4, beating Earth's atmosphere. because even when the air does let light through, we still have a major problem to solve.
Launching massive, fragile mirrors into the freezing vacuum of space is incredibly expensive, super risky, and you're totally limited by whatever can fit neatly inside a rocket fairing. So ground-based astronomers had to ask a seemingly impossible question. How do you fix a blurry sky? How can we get perfect, space-like optical clarity from right down here on Earth while looking up through miles and miles of swirling, turbulent air that constantly makes stars twinkle and blur?
Well, the mind-blowing, almost sci-fi solution to this is called adaptive optics. Here's how it goes. We literally fire powerful lasers 90 kilometers straight up into the sky to hit a natural layer of sodium atoms. This causes them to glow, creating a perfectly bright artificial guide star. We then point our sensors at that fake star, measure exactly how the turbulent atmosphere is making it twinkle and distort, and feed that data into a supercomputer. That computer then commands a network of microscopic actuators to physically warp and deform our telescope's secondary mirrors hundreds of times every single second. We are actively matching and canceling out the atmospheric turbulence in real time. We are literally unblurring the sky mechanically. It is wild.
Which brings us to Section 5, the ultimate cosmic observatories. This perfect escalation of technology leads us right into the modern era and the next generation of absolute mega machines.
That enormous astronomical number, 39.3 meters, is the diameter of the primary mirror for the Extremely Large Telescope, or ELT, currently under construction in the high deserts of Chile. To put that massive scale into perspective, a 39.3-meter mirror is roughly the size of a 10-story building laid completely flat on the ground. Since you obviously can't build a single piece of glass that big, this mirror is made of 798 distinct hexagonal segments, all working perfectly in unison. When it's finished, this single engineering marvel is going to collect 100 million times more light than your naked eye. It will literally possess more light-collecting power than all previous professional ground-based telescopes in history, combined.
But the ELT isn't alone in this endeavor. This next generation of ground-based behemoths also includes the Giant Magellan Telescope and the proposed 30-meter telescope, or TMT. But here's the catch. Building structures of this staggering magnitude requires the absolute highest, driest, and clearest mountaintops on Earth. And this brings grand scientific ambition directly into contact with humanity and culture. The TMT project, for instance, proposed for the pristine summit of Mauna Kea in Hawaii, faces ongoing cultural and legal opposition from native Hawaiian groups who consider the mountain deeply sacred. It's a really profound reminder that modern astronomy has to frequently navigate this complex, highly sensitive intersection of global scientific progress and local cultural heritage.
Now, if a 39-meter mirror somehow still isn't big enough to see the razor-sharp details you need, physicists use a technique called interferometry. By taking widely separated radio telescopes scattered across different continents, astronomers can record the light from the cosmos simultaneously. They mathematically link all these signals together using incredibly precise atomic clocks, because the data has to match up flawlessly down to the nanosecond. By doing this, these completely separate dishes function together as one enormous, virtually Earth-sized instrument. This mind-bending technique is exactly how the Event Horizon Telescope achieved the seemingly impossible, capturing the very first direct images of a supermassive black hole's shadow.
Yet, despite all of these monumental engineering triumphs, there is a deeply humbling truth we have to confront. Every single star you can see in the night sky, every planet we've discovered, the glowing gas clouds, the massive galaxies, heck, everything you and I are made of, all of that ordinary matter makes up only 5% of the entire universe. 5%! The overwhelming majority of the cosmos is entirely invisible to our instruments. It's made of invisible dark matter holding galaxies together, and the mysterious dark energy accelerating the expansion of the cosmos itself.
Which leaves us with this final provocative thought to take away from our explainer today. We started by looking at a tiny 7mm human eye, right? And we escalated all the way to global networks of atomic clock-synced radio dishes spanning the entire planet. But as we continue to build ever larger, more unbelievably complex observatories to peer into that invisible 95% of the unknown cosmos, what fundamental aspects of our reality will we test and perhaps completely shatter next? Thank you so much for exploring the physics of the cosmos with me today. Keep looking up and keep asking questions.